Good evening, everyone. Let's just wait for 5 minutes so that everyone can join. So, I hope you all must have watched the lecture videos. Last week we did some Laplace equations. I hope you are all well aware of how to solve the Laplace equation with some boundary conditions. If not, then also today we'll be solving some Laplace equations along with some boundary conditions. Okay, so let's start. Let's start with the first question. Solve the Laplace equation in a rectangle. So we are in a bounded domain. In the xy plane. So we are in R2. So we have two variables, xy plane with 0 less than x less than a and 0 less than y less than b. So our equation is uxx for every 0 less than x less than a, 0 less than y less than b, along with some boundary conditions. Ux at x comma 0 is 0 is equal to ux comma b for every 0 less than x less than equal to a, u 0 comma y equals to 0 for every 0 less than equal to y less than equal to b, and u at a comma y is equal to ky times b minus y. So it is a function of y for every 0 less than equal to y less than equal to b. So as we were doing earlier in the case of heat equation and wave equation, we'll be starting with a function uxy of the form xxyy, so that we can use the method of separation of variables, and more or less we will be using the same method that we had been using in the earlier classes as well, that is for the wave equation and heat equation. So let's just see how things are different in the case of Laplace equation. So I'll mark this as star. So let's solve it. I will start with taking uxy equals to, let uxy is equal to x a function of x and y a function only on of y. So let's number this as 1. Using first in star we get, so let's start with the boundary conditions. So we have 0 is equal to ux 0, x y 0 for every 0 less than equal to x less than equal to a. Now this gives us that y at 0 must be equal to 0, because otherwise the x will be 0 for every x, and that will give us the trivial solution. So for non-trivial solution we must have y at 0 is 0. Then we have u at x comma b 0, which is equal to x at x, y at b for every 0 less than equal to x less than a. So again this will give us y at b is 0. Let's mark this one as third. Then we have u 0 equals to u at 0 comma y, which is x at 0, y at b for every 0 less than equal to, sorry, this is y, for every 0 less than equal to y less than equal to b, and this gives us x at 0 is 0. Fourth. And the main equation uxx plus uyy equals to 0 gives us x double dash x xx is equal to y double dash y. So y double dash y. So this is y and this is x. So this basically gives us minus x double dash x by x is equal to y double dash y by y. Now on one side we have a function that depends completely on x, and on the other side we have a function in y, and they both are equal. So this is possible only if it is equal to, they both are equal to some constant lambda. So this gives us two second order homogeneous differential equations. First one is x double dash x plus lambda x is equal to 0. I'll mark it as equation fifth. And the other one is y double dash y minus lambda y equals to 0. I'll mark this as equation 6. Now we'll start with solving equation 6th. Now we will solve equation 6. So we can see that 6th is a second order homogeneous differential equation. We know how to solve such an equation. We solve it using the by finding the roots of the auxiliary equation. So here the auxiliary equation is the auxiliary equation for 6th is r square is equal to lambda. So now we'll look at the various cases, various possibilities for lambda. So case 1, when lambda is 0. In that case, we will get y equals to c1 plus c2. So you can see that by the conditions, boundary conditions on y, the equations second and third, from here you will get that by second and third we will get y equals to 0 for every y, and that will give us that u is a trivial solution, and we are searching for a non-trivial solution. So the second case will be when lambda is positive. In that case, we can write lambda equals to k square for some non-zero k. That will give us y is equal to c1 e to the power ky plus c2 e to the power minus ky. Again, using the fact that the exponential function is 1 1, and the using the boundary conditions and the fact that the exponential function is 1 to 1, you can see that this y will turn out to be a trivial solution. We will get y trivial solution, which will give us that u is a trivial solution. The third case will be when lambda is negative. That is, lambda is equal to minus k square for some non-zero k. In that case, we will get r is equal to plus minus k iota. That gives us y is equal to c1 sine ky plus c2 cos ky. That now now let's look at the boundary condition. By second, we have 0 equals to y at 0, which is just c2, and by third we will get 0 equals to y at b, which is c1 sine kb. Now to get a non-trivial solution, we must have kb equals to n pi, or c1 to be non-zero. Otherwise, if we get c1 0, again we'll end up having just a trivial solution. So this gives us k equals to n pi by b. Therefore, for lambda n equals to n pi minus n pi by b whole square, equation 6 has a non-trivial solution. Sixth has a non-trivial solution. Trivial solution given by y and y is equal to some constant c in times sine um, n pi by b y. Now let's solve equation fifth corresponding to lambda equals to lambda n. Now let us solve equation sixth corresponding to lambda equals to lambda n, which is minus n pi by b whole square. So let xn satisfies equation sixth corresponding to lambda equals to lambda n. This gives us xn double dash plus lambda n xn is equal to 0. So again, this is a second order homogeneous differential equation with constant coefficients. So its auxiliary equation is r square equals to minus lambda n. Minus lambda n would be n pi by b square. This gives us x is equal to c1, or I'll write it as some a n e to the power n pi by b plus bn e to the power minus n pi by b. Now we had a condition on x as well. So by equation 6, because xn is basically a solution of equation 5th, so a solution of equation 5 must satisfy the initial condition x0 equals to 0. So we have by equation 4, 0 is equal to xn at 0, which is just an plus bn. Now this gives us bn is equal to minus an. Therefore, xn x is equal to an times e to the power n pi, sorry, this is here we have x also well. So n pi by bx minus e to the power minus n pi by b x. So this gives us un x comma y is equal to, second, yn y times xn x is a non-trivial solution of star. Now by the principle of superposition, by the principle of superposition, the solution for our problem star is given by uxy equal to summation n from 1 to infinity unxy. So I'll just combine all the coefficients and write it as some other dn times e to the power n pi by bx minus e to the power minus n pi by bx times sine n pi by by. So if you remember the definition of hyperbolic functions, so we can write it as summation n from 1 to infinity 2 dn sine hyperbolic x times sine n pi by b y. So till now we have used the first three boundary condition. We haven't used the last one, so let's use that. We are given that u at a comma y is ky times b minus y. So now by star we have ky times b minus y is equal to u at a comma y, which is summation n from 1 to infinity. So this is not x, this is n pi by b times x 2 dn sine hyperbolic n pi a by b times sine n pi by b y. Now from here we know how to evaluate these coefficients dn. So this implies 2 dn times sine hyperbolic n pi a by b is equal to integration. So value of a is from 0 to b, the function ky b minus y times sine n pi by b times y dy by integration 0 to b sine square n pi by b y. So you can easily evaluate the denominator. It will turn out to be equal to b by 2. So this gives us b dn sine hyperbolic n pi a by b is equal to integration 0 to b ky b minus ky square times sine n pi by by dy. We have just multiplied both the sides by b by 2. Now we'll be using integration by parts to solve this integral. Moreover, I could just take this k also outside on the other side denominator. This is by minus y square. So by integration by parts, by minus y square as it is, integration of sine x is cos minus cos x. So this is minus cos n pi y by b by n pi times b limit 0 to b minus integration 0 to b derivative of the first part. This is b minus 2y. Integration of sine is again minus cos n pi by by n pi b dy. So we can see that once we put the limit y equals to b, this is 0, y equals to 0, again 0. So the first term vanishes. We are left with b by n pi. Again, we'll be applying the integration by parts. So this is b minus 2y as it is. Integration of cos is sine n pi by b times y by n pi times b, limit 0 to b, minus integration 0 to b. Derivative of minus 2y is minus 2. Integration of cos is sine n pi by b y by n pi times b dy. Now since sine n pi is 0, sine 0 is 0, the first term again vanishes out. We are left with 2b square n square pi square, and integration of sine is minus cos n pi y by b. So this is, or we can write it as just b cube by n cube pi cube, limits 0 to b. So this is 2b cube by n cube pi cube, cos 0 is 1, and cos n pi is minus 1 to the power n, which is equal to 0 when n is even, and this is equal to 4b cube by n cube pi cube when n is odd. So the left hand side was, just copy it, copy, so this is equal to 0 when n is even, 4b cube by n cube pi cube when n is odd. So this gives us dn is equal to 0 when n is even, and this is 4k b square by n cube pi cube sine hyperbolic n pi a by b when n is odd. Therefore, uxy is equal to summation, or we can just replace n by 2n plus 1 because at all the even points it is 0. So I'll write it as d 2n plus 1. So what was the rest of the terms? So I'll just replace n by 2n plus 1 from everywhere. So this is sine hyperbolic 2n plus 1. So this was sine hyperbolic n pi x by b. So this will be 2n plus 1 pi x by b with sine, the other term was n pi 2n plus 1 pi y by b, which is summation to infinity 8kb square by 2n plus 1 cube pi cube sine hyperbolic 2n plus 1 pi a by b times sine hyperbolic 2n plus 1 pi x by b times sine 2n plus 1 pi y by b. This is a final solution. I hope this solution was fine with everyone. I would like you to go through it once again. Uh, yes. And if you have any doubt, please let me know. Next, we have a similar type of problem. So I would like you to try it first. Then I will give you the solution. Question number 2. Find the solution of the boundary value problem. Uxx plus uyy equals to 0 for every 0 less than x less than a, 0 less than y less than b, along with the boundary conditions u at 0 comma y equals to u at a comma y. For every 0 less than equal to y less than equal to b, uy at x comma b is equal to 0. For every 0 less than equal to x less than equal to a, and ux comma 0 is equal to 100 for every 0 less than equal to x less than equal to a. So a similar procedure can be followed to solve this problem. I'll wait for 5 to 10 minutes and I want you to solve this first. Just try to follow the similar procedure as we had done in the previous question. In the last question, I have proved everything in detail. So I would like you to just go through that for this problem and try to find the solution. So again, we'll start with taking uxy to be some function multiple of some functions x and y. I'll mark this as number 1. Using first in star, we get, so by the boundary conditions, we will get x at 0 is equal to 0 is equal to x at a. The first boundary condition will give us this condition. The second one will give us that y dash at point B is 0. Condition third. And the third condition will be using at the end. And by the equation, from the equation uxx plus uyy equals to 0, we will get, and we have x double dash x by xx is equal to minus y double dash y by y. Now, since on one side of the equation we have a function in x, while on the other we have a function completely depending only on y, since these both are equal, they must be equal to some parameter lambda, some constant lambda. So this gives us two second order homogeneous differential equations with two constant coefficients, x double dash minus lambda x equals to 0. And so I'll mark this one as equation 4th, and y double dash y plus lambda times y equals to 0. So you might be wondering that why we took this minus with y, whereas in the last question we took it with x. Remember, we took this minus sign here with x, but in this case we are taking it with y. It is just because of the boundary conditions, because earlier we had these two where we have these two equations for corresponding to the function y, but this time we have these corresponding to the function x. So we will be taking this minus sign, so that we have corresponding to x we have some equation of this form. This is the standard form. We all have done such type of problem. These are called Sturm-Liouville problems, so that we get a Sturm-Liouville kind of problem in variable x, and we again go through the same cases and find solutions, or whatever we had done earlier, similar things. So that is why we took this minus here. So now we'll solve. Solving for, as done in previous problems, we know that by the boundary condition second, fourth will have a non-trivial solution only if lambda is negative, that is lambda is equal to minus a square for some k non-zero, and in that case our solution will be, and x will be some c1 times cos kx plus c2 times sin kx. Now the boundary condition second will give us, since x at 0 is 0, we will get x at 0 is c1. c1 is 0 and x at a is also 0. So we will get 0 equals to c2 sine ka. So we will get non-trivial solution only if this ka equals to some n pi. This x will be non-trivial only if ka is equal to n pi. Therefore, for lambda n equals to minus n pi by k whole square, we get non-trivial solution x n x equals to some cn times sine n pi by k, sorry, n pi by a. N by a. This is a solution of equation 4th. Now solving equation 5th corresponding to lambda equals to lambda n, we have y n double dash plus lambda n means minus n pi by a whole square yn y, this is y, equals to 0, and from here we will get yn y is equal to e to the power some an times e to the power n pi by a y plus bn times e to the power n pi by a minus y. So we had some initial condition for y as well. By equation 3rd, we have y dash b equals to 0. So let's find the derivative first. Yn dash is equal to an n pi by a e to the power n pi by a times y minus n pi by a bn times e to the power minus n pi by a, so by y. So from here, by equation 3rd, we have 0 is equal to yn dash b is equal to n pi by a times an e to the power n pi by a b minus n pi by a bn e to the power minus n pi by a b. Now this gives us bn is equal to, this n pi by a will vanish because since n pi by a is non-zero, we have the rest of the term an times e to the power n pi by a times b minus bn times e to the power minus n pi by a b will be 0, and that gives us bn equals to an e to the power 2 n pi by a b. Therefore, y is equal to, let's take this an to be common outside, e to the power n pi by a y plus e to the power n pi by a common 2b by 2b minus y. So this is our yn. Therefore, uxy equals to xn x times yn y is a solution of star, and hence by the principle of superposition uxy is equal to summation n from 1 to infinity. I'll take some other coefficient dn times e to the power n pi by a y plus e to the power n pi by a 2b minus y times, so what was xn? Sin n pi by sin, sin n pi x by a. Sin n pi x by a. So we are left with just one boundary condition, initial condition, boundary condition, ux 0 equals to 100. Boundary condition. So again by star we have 100 is equal to ux comma 0, which is equal to summation n from 1 to infinity y equals to 0. We have dn 1 plus e to the power 2n pi b by a times sin n pi x by a. So from here we get dn 1 plus e to the power 2n pi b by a is equal to integration 0 to, so x is from 0 to a, 0 to a 100 times sin n pi x by a dx by 0 to a sin square n pi x by a dx. So we know that this denominator will turn out to be just a by 2. So this is, I'll just multiply by a by 2 on both the sides. We have a by 2 dn 1 plus e to the power 2n pi b by a is equal to, let's take this 100 as well on the other side, 0 to a sin n pi x by a dx, which is minus a by n pi cos n pi x by a 0 to a. And this is equal to minus a by n pi, cos n pi is minus 1 to the power n, minus cos 0 is 1. So we have, this is equal to 0 when n is even, and this is equal to 2 a by n pi when n is odd. So from here we get d equals to 0 when n is even, and it is 2 into 200, 400. E gets cancelled out by n pi 1 plus e to the power 2n pi b by a. When n is odd. So this implies uxy is just summation n from 1 to infinity d 2n plus 1. So I'll take this n from 0 to 1. d2n plus 1 e to the power 2n plus 1 pi y by a minus e to the power 2n plus 1 pi by a times 2b minus y sine 2n plus 1 pi x by a. So basically we have just replaced, we are just taking the odd terms because we know that dn is 0 for all even n. So this is summation n from 0 to infinity 400 by 2n plus 1 pi 1 plus e to the power 2 2n plus 1 pi b by a times this same term. Paste. I don't know about this issue. I think there is some problem with my iPad. What's happening? So this is 2n plus 1 pi b by a times this same term. So this gives our solution. I hope this is fine with everyone. If you have any doubt, please let me know in any step. Please go through the solution once again. Then again we'll be solving Laplace equation with uh, till now we were working on some bounded domain. In next question we'll see whether we can work on some uh, infinite strip kind of thing. That means either x or y, either of one of them is bounded and the other one is can go to infinity. So you can see that we have exponential term. So we'll see that in next question. Please go through the solution once again. If you have doubt, please let me know. So then after some time we'll go to the next question. Please go through the calculations once again. There might be some mistakes. So this is what I have done according to me it should be correct, but you all must cross verify it. So let's get to the next question. This one I would like you to start solving first. Uh, up till let me write it. Find the solution of the following boundary value problem. Uxx plus uyy equals to 0 for x between 0 and 10 and y is in whole of R. So we can see that our domain is a strip, is an infinite strip. X is restricted from 0 to 10 and y can be any real number. So our domain is something like this. Along with the boundary conditions, u0y equals to 0 is equal to u10y. So this condition must have told you where should we keep that minus every y in R. The next condition is yx infinity equals to 0. So instead of writing y u at x comma infinity, it is better to write limit y tending to infinity uxy is 0 for every 0 less than x less than equal to 10, and the final last boundary condition is ux0 equals to some function gx, which is equal to 20x 0 less than equal to, let me just move this a bit, 0 less than equal to x less than equal to 5, 20 10 times 10 minus x, 5 less than equal to x less than equal to 10. So I would like you to start solving it. Take uxy equals to xxyy. Then using that, try to find the conditions that we can get on x. That means from this equation you will get that x at 0 is 0, x at 10 is 0. Using these two conditions and putting ux y in the equation uxx plus uyy equals to 0, taking the function depending on x on other one side, depending on y on the other, and equating it with lambda, taking minus accurately on which side you must take, so that you get a Sturm-Liouville kind of problem, which can be solved using the conditions x0 is equal to 0 and x at 10 is equal to 0. And then after taking the three cases, you try to find what will be xx. After that, I'll solve. So please reach till the point where you will get for lambda n equals to, so here you will get lambda n equals to minus n pi by 10 whole square. Try to get x n x is equal to sine n pi by 10 x. I want you to solve this yourself. I'll give you 10 to 15 minutes. After that, we'll see how to uh, tackle this problem of limit y tending to infinity and other things. So I hope you must have got this xn and lambda n. So we have the boundary condition, limit y tending to infinity u x y equals to 0. This gives us 0 is equal to limit y tending to infinity u x y for every xn. So for every 0 less than x less than 10 x. So this is limit y tending to infinity. So what is xy? X x y y. So this is x x times limit y tending to infinity y y for every 0 less than x less than 10. So this gives us, again, since x is non-trivial, we get limit y tending to infinity y y is 0. So this will act as a boundary condition for us now. So after finding this xn, so the other equation that we needed to solve was, so this must have been solution of, we had x double dash minus lambda x equals to 0, and along with that we had another equation. Now let us solve. The other equation is y double dash plus lambda y equals to 0, corresponding to lambda equals to lambda n, and lambda n is minus n pi by 10 square. So again, this is a second order homogeneous differential equation with constant coefficients. So from here we can solve it by finding the roots of the auxiliary equation. The auxiliary equation is r square equals to minus lambda, that will be n pi by 10 whole square. So that will give us y n y is equal to n times e to the power n pi by 10 y plus bn times e to the power minus n pi by 10 y. Let me mark this as 1. By first, we have 0 is equal to limit y tending to infinity y y. Now this is limit y tending to infinity a n e to the power n pi by 10 y plus, I can write it as plus 0, because we know that limit extending to infinity e to the power minus x is 0. So from here we must have an is equal to 0, because if an is non-zero, in that case this limit y tending to infinity of yn will tend to infinity. Yes, if an is non-zero, in that case limit y tending to infinity a n e to the power n pi by 10 y, because this is positive, will be infinity, and that's not the case now. This is equal to 0, therefore a n must be 0. This implies that y n y is equal to bn times e to the power minus n pi by 10 y. Therefore u n x y, which is some other constant coefficient dn times e to the power minus n pi by 10 y times sine n pi by 10 x is a solution of given Laplace equation. Therefore by the principle of superposition, we have uxy is equal to summation n from 1 to infinity dn e to the power minus n pi by 10y sine n pi by 10x. Now we had another boundary condition, the last one, ux0 is gx. So by star gx is equal to ux0, such as summation n from 1 to infinity dn e to the power 0 is 1, so we have just sine n pi by 10x. So from here we know how to evaluate this dn. This is integration 0 to, now value of x is from 0 to 10. So we'll integrate x from 0 to 10 gx times sine n pi by 10x dx, and we know the denominator will be 10 by 2 in this case, that will be 5. So this implies 5 dn is equal to, now gx is a piecewise function. The first part is from 0 to 5. This is 0 to 5, 20 sine n pi by 10x. So let's not take this 5 that side. This is 1 by 5 plus 1 by 5, 5 to 10, 20, 10 minus x sine n pi by 10x dx. So I hope you can just integrate this using integration by parts, and this will turn out to be, so this is 4 minus cos n pi by 10x 0 to 5 n pi 40 plus 4. Now here we will be using integration by parts. So this is 5 to 10 minus integration 5 to 10 minus 1 plus cos n pi by 10x by n pi 10. So you can just evaluate it, and at the end you will get this is equal to 800 by n square pi square sine n pi by 2. So this is 0 when n is even. This is 800 by n square pi square, where n is of the form 4k plus 1, and this is minus 800 by n square pi square, where n is of the form 4k plus 3. So this is our dn. You can just go through this integral once again. So the main important thing was to understand this limit boundary condition. The rest of the things were similar as we have been doing in earlier questions. Just be careful about the calculations. Go through the solution once again. If you have any doubt, please let me know. After that, next we will be working on some uh, problems of Laplace equation in radial form. So instead of x and y, we will be having we will be working with r and theta. Circular planes. Please go through the solution again. I'll wait for 5 minutes. If you have any doubts, please let me know. So let's move to the radial form of the Laplace equation. Question number 4. Find the solution of of the following boundary value problem. URR plus 1 by r times UR plus 1 by r square u theta theta equals to 0, along with the boundary conditions. UR is equal to 0 is equal to u r pi. That means this is for every r positive and 0 less than theta less than pi. And then we have this is for every r positive. Along with this we have u 0 comma theta equals to 0 for every 0 less than theta less than pi, and u at 10 comma theta. Oh, sorry. So r is from 0 to 10. So this is 0 less than r less than 10. Let's put r less than equal to 10. This is 50 theta is for all theta between 0 and pi by 2, and this is 50 times pi minus theta for all pi by 2 less than theta less than equal to pi. Solution, we will take u r theta is equal to product of some function r that depends on r with some function capital theta that depends on variable theta. So let's mark this as star, this as first. Using first in star, we get r double dash r plus 1 by r dash r times theta theta plus theta double dash theta by r square times r is equal to 0. Now again we'll take the function depending the part depending on r on one side and the part depending on theta on the other side of the equation. So from here we will get minus r double dash r by r or right, r double dash r plus 1 by r dash r times r square by r capital R is equal to theta double dash theta by theta. So now on the left hand side we have a function in r, whereas on the right hand side we have a function of theta. Since these both are equal, they must be equal to some constant lambda. So this gives us r square r double dash plus r dash minus lambda plus lambda r is equal to 0. I will mark this as second, and we have theta double dash theta minus lambda theta theta equal to 0. And by the boundary conditions, we will get the boundary conditions again. We will get r0 is equal to 0 is equal to r pi sorry theta theta. That is for all r. So we have theta 0 is equal to 0 is equal to theta pi. So this is this system. Third, fourth is again a stum Liverly kind of problem. You can solve it by taking various different cases for theta, lambda, and again you will end up with the fact that this problem will have non-trivial solution in only in the case lambda non-zero, lambda negative, and so using the techniques as done in previous problems, we will get theta, we will get second problem, the equation third will have non-trivial solution for lambda n equals to, so please solve this as we have been doing earlier. I'll just give you the solution. So for lambda n equals to minus n square, we will get a non-trivial solution for equation third, and theta n, theta will be, so this is cn times sine n theta. So I'll wait for 5 minutes. Please do this yourself. I think you will not have any problem in solving this and getting the same solution. So I hope you can do that yourself. So now corresponding to this lambda n, we will solve equation second. Now solving equation 2 corresponding to lambda equals to lambda n, which is minus n square. So we have r square r n double dash plus r r n dash minus n square r n equals to 0. So if you remember, this is a homogeneous second order differential equation with a non-constant coefficient. So this is basically a Euler kind of equation. So to solve this problem, we start with the substitution. Z equals to ln r, and this will give us that drn by dr is nothing but 1 by r times drn by dz. Next step we will be using the product rule to find d2rn by dr square. So here we will get minus 1 by r square times drn by dz plus 1 by r square times d2rn by dz square. Now substituting these values in the equation, we will get rn double dash minus n square rn equals to 0. If you remember, we had done similar kind of problems in the starting of the session. So now again, we are in the setup of second order homogeneous differential equation with constant coefficients. We can find the solution by finding the roots, and in this case roots of the auxiliary equation, and in this case we will get our auxiliary equation is m square is equal to n square, m is equal to plus minus n. So we get rn depending on variable z is equal to c1, or let's write it as an times e to the power nz plus bn times e to the power minus nz. Now we know that e to the power z is r. So from here we get r and r is equal to an r to the power n plus bn r to the power minus n. Now let's see whether we have some boundary condition for r. So yes, from since u0 theta is 0 for every theta, we have absence by star. We have 0 is equal to u0 theta, which is r theta theta for every 0 less than theta less than pi. We get, sorry, this is r0. R at 0 is 0. Therefore 0 is equal to Rn0, which is equal to An plus Bn. So this gives us Bn is minus A. So this implies Rn R is equal to An times Rn minus R to the power minus A. So therefore UNR theta, which is equal to, I'll take some other coefficient dn, which is basically an times cn, dn times r to the power n minus r to the power minus n sine n pi theta. So that was n theta, sorry, not pi. So this is sine n theta. Is a non-trivial non-trivial solution to the given Laplace equation. And hence by the principle of superposition, u r theta equal to summation n from 1 to infinity dn r to the power n minus r to the power minus n sine n theta. So now we had one more boundary condition. We had now by star we have g theta. So did I mark it as function g? So let's define this equals to function g theta. So this is g theta is equal to u10 comma theta, which is summation n from 1 to infinity dn. Putting r equals to 10, this is 10 to the power n minus 10 to the power minus n sine n theta. So from here we know how to evaluate its coefficient dn times 10 to the power n minus 10 to the power minus n. This is integration 0 to pi, because theta varies from 0 to pi, g theta times sine n theta by 0 to pi sine square n theta d theta. We know that this denominator will turn out to be pi by 2. So this is just let me take this pi. Let me just multiply on both the sides with pi by 2. This is pi by 2 dn 10 to the power n minus 10 to the power minus n is equal to, now this g is a piecewise function. This is 0 to pi by 2 50 theta sine n theta plus pi by 2 to pi. This is 50 pi minus 500. Oh, no, not 500. That's 50 theta sine n theta d theta. So we basically need to use the integration by parts. So this is 50 theta as it is cos n theta by n minus 0 to pi by 2 minus integration 0 to pi by 2 50 cos n theta by n d theta. Plus 50 pi minus theta minus cos n theta by n pi by 2 to pi minus integration pi by 2 to pi 50 minus 50 cos n theta plus by n d theta. So this is minus 15, putting theta equals to pi by 2 n cos n pi by 2. Putting theta equals to 0, it will be 0 plus 50 by n sine n theta. So this will be n square, 0 to pi by 2. Now in the next term, if we put theta equals to pi, this is 0. And for theta equals to pi by 2, this is 50 pi by 2n cos n pi by 2 minus 50 by n square sine n theta pi by 2 to pi. So this gets cancelled out. This is 50 by n square sine n pi by 2, because since sine 0 is 0, the lower limit will be 0, minus again sine n pi is 0, so this is 0 minus sine n pi by 2. This is just 100 sine n pi by 2 by n square, which is 0 if n is even. This is 100 by n square if n is of the form 4k plus 1, and this is minus 100 by n square if n is of the form 4k plus 3. So from here we get dn, just divided by terms. So from here we get dn is equal to 0 when n is even. Then we have 100 by, so this will be 200 by pi n square 10 to the power n minus 10 to the power minus n when n is of the form 4k plus 1, and it will be minus 200 by n square pi 10 to the power n minus 10 to the power minus n when n is of the form 4k plus 3. So this gives our coefficient dn, and we can put this coefficient back to the series to get the explicit form of this solution. So I hope this solution was fine with everyone. If you have any doubt, please let me know. Using similar approach, I would give this as a homework. You can solve this Laplace equation in the radial form. Find the solution of the boundary value problem URR plus 1 by R UR plus 1 by R square U theta equals to 0, along with the boundary condition UR is 0 equals to UR pi and U A theta equals to U naught. So in this case, you may not be able to evaluate the coefficients, but before that, till that, you can find a general solution. So I would like you to try this problem yourself, and we'll meet next Friday. If you have any doubt while if you are stuck somewhere while solving this problem, you can ask me once the class starts. Okay, then we'll meet next Friday. Thank you so much.